Hi, everybody. Welcome back to Dave's Math channel. This is my sixth video and a new feature I'm doing on my three-volume series, which I published in 2022 called the Math Lovers Book. In case you guys are interested, you can, these are available on Amazon.com. You can look for my name, David Tare, or you can type the Math Lovers Book, and I'm sure this will come up. And like I said, there's three volumes. You can buy them individually or any combination or as an entire package. And just give you a little overview. The first book that's the one I'm going over right now. That's volume one, which is more recreational. These are all textbooks, and the first one is more recreational, kind of fun math, fun topics, I think. But it is kind of advanced high school level. It's like I said, the math lovers book. It's for people who already like math, or but even better, love math. I think math is beautiful. It's like art, and I think that's kind of the point of view I conveyed throughout this series. Um, it's got several topics on recreational math that aren't usually addressed, at least not in detail in school, but I think they're fun and they're also important. Uh, the second volume is more academic. This is more. It's also a little bit more advanced. It's kind of like undergraduate level math that includes calculus as well as I guess pre-calc. Functions, theory of functions, and also I think. Um, Fractals and chaos, and at the very end, it has a section on the biographies of famous mathematicians. And I decided that every week I'm gonna do that in addition to what I'm doing right now, which is just presenting lessons from my book every week. I'm not sure which day of the week. Maybe I'll start tomorrow. I mean, the lesson I'm doing today is the last lesson in chapter one of volume one, so it's probably a natural place to, or at least section one of volume one. At least it's probably a natural place for me to, present my first biography. And I've got 80 biographies of 80 famous mathematicians throughout history in chronological order. Going back all the way from ancient times up to the present. So I think that'll be kind of interesting to kind of talk about a lot of these famous mathematicians, what they did, and why their work was important. And so that's volume two. Volume three is problems and solutions. So there are kind of exercises I go through in each of the first two volumes, but then I also give problems in the yellow book, the problems and solutions manual. It starts with a bunch of problems pertaining to each section in the first two books, and then there's after that there's solutions to all the odd number problems. I don't give solutions to the even number problems because I like you to have some problems you can do yourself without having to look up the answer. That's kind of like cheating. In real life, you're not always given the answers. Anyway, so that's an overview of the Math Lovers book. I think you guys will enjoy it. And like I said, I'm doing a free feature here. I'm doing free videos on video lectures on every lesson in this series. So today I'm up to, I've been talking about different types of bases. I think you guys are all familiar with decimal base 10. That's our usual counting system, but there's other bases as well. Two of the most common I already talked about, binary. That's the one that's used by computers. All the numbers that are stored inside a computer are binary numbers. The digits, they're called bits. They're all 0 or 1. Those are binary digits. And then there's hexadecimal, which is more compact, but it's basically like binary. You just use a hexadecimal digit in place of 4 bits. So I talked about those two already. Today I'm going to talk about general bases, other bases. It turns out you can have any base you want. The base can be any natural number, 2 or larger. 2 is the smallest, that's binary. So I'm going to talk about that today. So anyway, let's begin. So I think I already kind of gave you an overview of other bases. And I think, we've already seen a couple examples. We've seen base 2 where the digits are the bits. We call them are either 0 or 1. We saw hexadecimal where the bits are 0 through 9 as well as A through F. We had to start using letters beyond 10 because 16 is bigger than 10. Decimal has the digits 0 through 9. If the base is less than 9, we just use the decimal digits, but we stop at b minus 1. Just like for base 2, we stopped at 1. For base 3, we would have 0, 1, and 2. For base 4, we'd have 0, 1, 2, and 3, so on. But then when you go beyond 10, you have to add additional symbols, and what we do is we add letters, and there's 26 letters in the Roman alphabet, which allows us to go up to base 36 using this system. Base 36 would start with all the digits 0 through 9 and end with all the letters A through Z. Z would represent 35. I think you get the idea. So what do we do beyond base 36? Well, then we have to, we don't have any choice but to use more than one symbol. We could keep using more symbols, but it would get so complicated. I think it's better to just use multiple symbols for each digit in this system, and we separate them by commas. So I think I talked about sexagesimal algebraic base 60. That's what the Babylonians used. And the way I described, sexagesimal is actually the way the Babylonians did this. They did use two symbols for each digit in your system, which was a number from 0 to 59. They didn't have a symbol for 0, but they had symbols for 1 through 59, which is just based on wedges. And you can think of those as two symbols, where the symbol on the right was a decimal digit 0 through 9, but then when you went beyond 9, the second digit, the second subdigit, if you like, the symbol next to the one on the right was sort of like the tens column, but only went up to 5. So that if you combine those two symbols, you would get numbers from 0 to 59. But then when you go beyond 59, you go to the next place, which is the next set of symbols past the comma. I think this will make more sense as I do more examples. But anyway, that's how we represent numbers in different bases, and you can have arbitrary bases, and it's rare to go beyond base 36 anyway. I mean, base 60 is a nice base, but you very rarely see big bases. Hexadecimal is pretty big too. But anyway, that's bases. And so, and we convert from an arbitrary base to decimal. I already showed you how to do that in base 2, binary, as well as hexadecimal. You can do it on any base you want. Just the same idea. It's just that you have to use your base, B. We usually call B the base. So in this case, here's an example in base 5. And by the way, I don't think I mentioned this yet, but when you write a number in a given base, it's customary to use a subscript at the end of the number. So the number ends with a subscript, which indicates the base. So for this example, we're looking at the base 5 number 42103. And then that subscript 5 just means that you're supposed to interpret that number as a number in base 5. So suppose we wanted to convert this number to decimal. What would we do? Well, it's the same idea we've been doing before. Notice that this number has 5 by base 5 digits. So the one on the right is the ones column, if you like. The one next to it is the fives. The one next to that to the left. We keep going from right to left. The third one from the right, or the second one from the right is 5 squared. The third one from the right is 5 cubed, and the one on the left, or the fourth from right, if you like, is 5 to the fourth. So the way we interpret this number, we read off each digit of the number. So the first digit is 4, and then we multiply that by its place, which in this case is 5 to the fourth. And then we keep going. The next digit is a 2, so we add 2 times, in this case 5 cubed, because now we're in the 5 cubed place. And then we keep going, plus 1 times 5 squared, plus 0 times 5 to the 1. If you like, you can ignore that because it's a 0, but it's a little more transparent if you write each one. And then the last one is 3 times 5 to the 0, or just 3. So you simplify this. I'm not going to have to go through all the steps of simplifying it, but when you do all the arithmetic, what you end up was 2,778. So that's what this number is in decimal. And you probably noticed something already. I didn't point this out yet, but when you write numbers in a given base, you'll notice that the numbers always look bigger the smaller the base is. And this base 5 is less than base 10. That's why it looks like a bigger number when we write it in base 5 than it does in base 10. And conversely, if you write a number in a bigger base than 10, it looks smaller, but you have more symbols. So it really conveys the same amount of information. It's just that since you're allowing more symbols, I guess the information is more compact, but it kind of looks like a smaller number, but there's really a trade-off in the number of symbols. And the reason binary numbers are so big is because you're only using two symbols, right? You can't give me that much information with just one bit, a 0 or 1, whereas you can convey with a decimal digit. I'm kind of jumping the gun here. If you want to go into information theory, the number of bits of each digit, a decimal digit is the base 2 logarithm of 10, which is about 3.3, I think. So a decimal digit is about 3.3 bits. Yeah, you get the same number of bits in a number no matter what base you write it in. Anyway, that's kind of a digression. But anyway, I did another example below. Here's a base that's bigger than 10 on the bottom. We have this is what's called duodecimal or base 12. And I think base 12 is a really interesting base, by the way. As a matter of fact, there was a kind of a push for a while to start using base 12 instead of base 10. And maybe someday we will. I think probably in another 2 or 3 centuries. I don't think we'll be using decimal anymore. The only reason we use decimals, we have 10 fingers, but base 10 isn't a very good base. I mean, 10 doesn't have that many factors. It has 4 factors: 1, 2, 5, and 10. Whereas 12 has 6 factors: 1, 2, 3, 4, 6, and 12. That means it's a lot easier to divide in base 12 because you can divide by 2, 3, or 4, or 6. And you got a terminating decimal, whereas in decimal you can only divide by 2 and 5. Base 6 turns out to be pretty good too. Another good base, like I mentioned earlier, is base 60. But base 10 really isn't that good a base. And we only use it because we have 10 fingers. And I don't know what's going to happen in the future. Maybe we'll be genetically modified to have 12 fingers, or else we'll just learn to count without using our fingers. Anyway, you guys can think about that. But for now, we're stuck with decimal because it's what everybody uses. But anyway, so now let's here we have a duodecimal number 3A48, and we want to convert this to decimal. Well, same idea again, except this time we're using powers of 12. So this one has 4 duodecimal digits. So the one on the left is the 12 cubed column. So we write 3 times 12 cubed. The next one's an A. And here we have to remember that the letters stand for numbers. We just using, a letter because otherwise if we wrote them in decimal, we'd have to use 2 symbols. So A represents 10. So then the second number is 10 times 12 squared. And then the third one's a 4. We don't worry about that. 4 times 10, 12 to 1. And the last one's an 8. So that's just 8 times 12 is 0. And when you do all the math, you get 6,680. So that's what this number is in decimal. Anyway. Okay, so anyway, that's how to convert arbitrary numbers and arbitrary bases to decimal. I think you got the idea. And going the other way, like I was in binary and hexadecimal, it's harder to go from decimal to an arbitrary base. But there are algorithms. I think for binary, I presented 2 algorithms. I call them the top-down algorithm and the bottom-up algorithm. Well, you can do the same thing on arbitrary bases. It's just that these algorithms become a little bit more complicated in arbitrary bases. They're kind of complicated algorithms. I mean, they're nice to write for computers. You can write computer code to convert from an arbitrary base or from decimal to an arbitrary base. The good news is this is kind of, we don't usually have to do this as humans much because the whole idea of using a different base is because it's more convenient. I mean, we wouldn't be using duodecimal unless we didn't like decimals. So if we were all using duodecimal, we wouldn't even really think of base 10 anymore, So we wouldn't really have to do the conversion back to base 10 or to base 12. But, if you're writing a computer program, you want to convert between bases, you do kind of have to know how to do this. So do I want to just kind of summarize this method? Maybe that's what I should do here. I'm not going to go through every step like a computer program, but basically the idea is the top-down method. Remember when I was talking about top-down and bottom-up and binary? Top-down just means you're reading the number you're given from the most significant digit, the digit on the left, all the way to the digit on the right, and you're converting from left to right. It turns out bottom up is simpler. Maybe top down's a little more intuitive, but bottom up is simpler. So, but the idea is that when you're reading a number in decimal, you want to find the biggest power of the base that's less than or equal to the number you're given. Remember, that's what we did in binary. So in that case, where we're doing powers of 2, I think we had an example with 345, and it turned out the biggest power of 2 that was less than or equal to that was 2 to the 8th, 256. So it's the same idea, except this time we're using, it's not quite like that because we have to use multiples of it too. So there's actually another step. But I think I'll just do an example. This is kind of complicated. Probably won't help you if I go over this algorithm because it's pretty complicated. But let's just look at an example here. So now the example we're going to start with is to find the base 8 representation of the number 627. I picked 627 because it's my birthday, June 27th. I like this number. And I see it a lot. I don't know what that means, but it just so many times I've looked at digital clocks and it's 627. I don't know what that means. I'm sure it's a lot more times than probability theory would allow. I don't know why, but maybe there's some kind of mystical or cosmic significance to that. I don't know. But anyway, so let's try to convert this number 627 to base 8, which is also called octal. And octal is another convenient base because it's a power of 2. 8 is a power of 2. And as a matter of fact, there were a lot of computer programmers that used to use octal. I don't think it's used so much anymore. I think now we use hexadecimal a lot more than octal. But I know that octal was used a fair amount, probably until about maybe 20 years ago. But anyway, let's just do this. So how will we do this? Well, let's start by looking for the biggest power of 8 that's less than or equal to 627. And that turns out to be 512, 8 cubed. And then we look for the biggest multiple of that that's still less than the number. In this case, we can't multiply it by anything without getting bigger than 627. So we stop at 512. That means that our first octal digit is a 1 because that's the multiple we used. So there's three octal digits of this number. No, there's 4 octal digits of this number because the highest power is 8 cubed. Remember, we start with 8 to the 0 on the right. So the most significant digit is going to be the 8 cubed digit, and it's a 1. So we write 1, and then what we do is we subtract 512 from 627. And if you do that, you'll get 115. And then you do the same game with 115, and then you look for the next biggest power of 8 that's less than or equal to 115. That happens to be 64, which is 8 squared. And again, you can't multiply by anything without going over 115. So that means your second octal digit is also a 1. So the number starts 1, 1. And then, you subtract 64 from 115, that'll give you 51. And then now the biggest power of 8 that's less than 51 is 8 itself. And then it turns out you can multiply 8 times 6. That gives you 48. So 6 is the biggest power of 8 that's less than or equal to 51. That means your third octal digit is going to be a 6. And then when you subtract 48 from 51, you're left with 3. And 3 is already less than 8. That means it's your last octal digit. So the number is going to be 1163 an octal. That's how you do that. Kind of complicated. But anyway, like I said, there's another algorithm called the bottom-up algorithm. And I don't know if you guys remember me talking about the bottom-up algorithm for going from decimal to binary, but it's the same idea. What you want to do in this case, remember in binary, we started by seeing whether the number was even or odd. Well, even or odd just means you're looking at the number modulo 2. I don't know how many of you guys are familiar with modular arithmetic. Modulus just means remainder. When you divide by a number, it's the remainder you get after you divide. So the idea in this case is that if you're trying to convert a decimal number to some arbitrary base b, you always want to start by computing the remainder of the number you have modulo b. In other words, the remainder you get if you divided the number by b. And that becomes your rightmost base b digit of the number. And then remember what we did when we were doing binary. The next thing you want to do is divide by b. If you like, you can subtract the digit you just wrote down and then divide by b, because then the number, if you first subtract it out, the number you're left with will be a multiple of b, so you can divide exactly by b. Or another way to think about it is you're taking the floor of the quotient of the number you started with divided by b. It won't in general be an integer. It'll only be an integer if the last base b digit you wrote down happened to be 0, which it usually isn't. But if you always take the floor, which means just round down, you will always get an integer, and then you just kind of proceed recursively. You do the same thing you did with the number you're left over with until you're left over with a number that's less than b, and that becomes the most significant base b digit of the result. So that, I think that's an easier example, and I think it's actually more efficient. If you're writing a computer program to convert a number from decimal to base b, this would be a more efficient method, I think, even for a computer. And it's also, I think, easier to implement. So let's try to do the same thing. Now I'm going to do the same algorithm again to convert the number 627 to octal. And let's see how that works now. So now our first step is going to be find the remainder when we divide 627 by 8. And you might think it's kind of hard to divide 627 by 8. And yeah, if you do long division, it is a little bit hard. But if you did it, then you would find that the remainder is 3. And I mean, I guess you have to calculate the quotient too. We might as well calculate the quotient. Turns out the quotient is going to be 77 and the remainder is going to be 3. So since the remainder is 3, that means our rightmost octal digit is a 3. And now we do the same game we did, except we start with 77. And 77, if you divide that by 8, you'll get 9 with a remainder of 5. So that, oh, is that right? Did I just do something wrong? 627 divided by 8. I might have made a mistake. Maybe I shouldn't do this in my head. Is that right? 640 divided by 8. Oh, it's 78. Yeah. Okay, so it's 78 with a remainder of 3. And then if you divide 78 by 8, you get 9 with a remainder of 6. So that means your second octal digit is a 6, second from the right. And that does agree with what we had before. Now you're left with 79. So then you divide 9 by 8. That gives you 1 with a remainder of 1. So that means this is the remainder is 1. That means our second octal digit's a 1. And then when you divide 9 by 1, finally you get 1. And that's the last thing you're left with. So you write a 1 as your last octal digit. So that's how you do it. And I think this is an easier algorithm. And I hope you guys understood what I just did. It might have been helpful if I drew some more helpful pictures here, but I kind of did this on the fly, just copied the pages from my book. And if you were reading my book, you'd have to read all this. Maybe I could have done some better illustrations. I don't know, but I spent 3 years writing this series, and it was a lot of work. And I would appreciate if some of you guys buy this thing, because I've hardly sold any copies. I'll just confide that in you right now. I know it's not good salesmanship to say that you're not selling your book, but I'm honest. I've always been honest. Maybe that's why I'm not a salesman or a businessman. I definitely don't think like Trump, and I'm glad I don't, because I think he's going down in flames, and hopefully we won't with him. But anyway, enough of that. So I think that concludes my video for today on arithmetic and arbitrary bases. Thank you for watching. Long live math, and I'll see you guys next time. Bye.